Energy has a tendency to hide from us, and we need thermometers and other instruments to make sure that it's still there. The first demonstration of the conservation of energy, the energy is conserved no matter how complex the process or no matter what, even when we don't know the detailed laws. The first demonstration of the law of conservation of energy, in fact, was not by a physicist but by a doctor, a medical man. He demonstrated with rats that the total energy of the food put in before and the heat generated you burn food and you find out how much heat is generated, and then you feed the rats the food, and it's converted an oxygen and it's converted to carbon dioxide the same way as in burning, and measure the energy in that case, and you find out that living creatures do exactly the same thing as non-living creatures. That the law of conservation of energy is exactly as true for life as not. As a matter of fact, it was discovered by this. Incidentally, it's interesting that every overall principle that we know that we can test on the great phenomena of life work just as well as for dead things. That is, there is no evidence yet that what goes on in living creatures is necessarily different, or maybe more complicated, but that is necessarily different than what goes on in non-living things. I mean in the physical, as far as the physical laws are concerned. Incidentally, this amount of energy that's in the food, it'll tell you how much heat and mechanical work and everything that's generated is what you read. When you hear about calories, you're not eating something called calories, but you're eating that measure of the amount of heat energy that's in the food. For people who physicists always feel so superior and smart and so on, that people would just like to get them once on something. And so I'll give you something to get them on. They should be utterly ashamed of themselves, because they take the same thing, energy, and they measure it in a host of different ways with different names. Absolutely absurd. Energy can be measured in calories, in ergs, in electron volts, in foot-pounds, in BTU, in horsepower hours, in kilowatt hours. All exactly the same thing. It's like having money, in dollars and in pounds and so on. But unlike the economic situation where the ratio can change, these dopey things are an absolutely guaranteed proportion. If anything could be analogous to it at all, the only hope would be to say that there are 20 shillings to a pound, and that you have shillings and pounds, with one complication that the physicist allows, and that instead of saying he has 20 shillings to a pound, he says he has irrational ratios like 1.6183178 shillings to a pound. So, in addition to that, you'd think that the more modern, high-class theoretical physicists would at least use a common unit, but you can find papers with degrees Kelvin for measuring energy, megacycles, inverse Fermis is the latest invention. We don't need any more inventions. We should all measure the energy in exactly the same. We should measure the energy in one unit and let it be done instead of having all these different names. And it just shows that people are often also, they want to say, see, I should bring my little boy to show on the screen so that the audience will understand that I'm human. Well, the proof that physicists are human is the idiocy of all the different units which they use in measuring energy. Now, we have a number of interesting phenomena in nature which present us some curious problems with energy. Has recently been discovered things called quasars, which are very far away and emit a lot of light. They're enormously far away, emit a lot of light and a lot of radio waves, and have radiating so much energy that the question is, where does it come from? That is, after it's radiated this enormous amount of energy, the condition must be different than it was before, if the conservation of energy is right. Question, is the thing collapsed gravitationally? Is it different condition gravitationally? Is it coming from gravity energy, this big emission? Or is it coming from nuclear energy and so on? And nobody knows. Will you like to propose that maybe the law of conservation of energy is not right? Well, when a thing is investigated as poorly, I don't mean as incompletely as is the quasars, because they can't see so easy at such a large distance, it very rarely is, when a thing looks difficult, that the fundamental laws are wrong. It's usually that the details are unknown. Another interesting example of the use of the conservation of energy is in this reaction. It was first thought that neutrons turn to protons plus electrons. But the energy of a neutron is fixed, and that of a proton could be measured, and the energy of an electron did not add up correctly to the energy of the neutron. If the proton and electron together didn't add up to the neutron. Two possibilities existed. One was the law of energy conservation is not right. In fact, it was proposed by Bohr for a while that maybe the conservation law worked only statistically on the average for large scale. But it turns out that Pauli suggested no, that the fact that the energy doesn't check out is because there's something else coming out, which we now call an antineutrino, and that this other thing coming out takes out the energy. You say the only reason for the antineutrino is to make the conservation of energy right. Well, it takes a lot of other things right. Conservation of momentum and other conservation laws are fixed up right because the piece came out that we weren't worrying about. And very recently it has been directly demonstrated that such neutrinos indeed exist. That illustrates a point. Why are we able to extend our laws to regions that we're not sure? How is it possible? Why are we so confident? Because we check the energy conservation here, then when we get a new phenomenon, we say it's got to satisfy the conservation of energy. And every once in a while you read in the paper that the physicists have discovered one of their favorite laws is wrong. It's not a mistake to say that it's true in a region where you don't look yet, when you haven't looked yet. If you will not say that it's true in a region that you haven't looked yet, you don't know anything. If the only laws that you find are those which you just finished observing, then you can't make any predictions, and the only utility of the science is to go on and to try to take guesses. You see, the most likely thing is that the energy is conserved in other places. So what we do always is to stick your neck out. People like this, and that of course means that the science is uncertain. The moment that you make a proposition that about a region of experience that you haven't directly seen, then you must be uncertain. But we always must make statements about the regions that we haven't seen, or is no use in the whole business. For instance, in early experiment, the mass of an object changes when it moves because of the conservation of energy. The energy associated with the motion appears as an extra mass because of the relation of mass and energy. So things get heavier when they move. It was first believed by Newton that this wasn't the case, that the masses stayed constant. And so when it was discovered that that was false, everybody say it was a terrible thing that physicists found out they were wrong. Why did they think they were right? The effect is very small. Only when you get near the speed of light does it make any difference. If you spin a top, it weighs the same as if you don't spin it within millions, very, very fine fraction. So you could say, oh, they should have said, if you do not move any faster than so-and-so, then the mass doesn't change. That would then be certain. No. The experiment happens to be done only with tops made out of wood, copper, steel, and so on. So we should have said that tops made out of copper, steel, wood, and so on were not moving any faster. You see, we do not know all the conditions that we need for an experiment. It is not known whether a radioactive top would have a mass that's conserved. But we have to take a guess. So in order to have any utility at all to the science, in order not simply to describe an experiment that's just been done, we have to propose laws beyond their range, and there's nothing wrong with that. That's the success. That's the point. And that makes the science uncertain. If you thought before that science was certain, well, that's just an error on your part. Now there are so we have here the energy, which we could put in our list. And it's conserved perfectly as far as we know, but it does not come in units. And now the question is it the source of a field? And the answer is yes. Einstein understood gravitation as being generated by energy. Energy and mass are equivalent, and Newton's interpretation that the mass is what produced the gravity has been modified to being the energy that produces the gravity. There are other laws that are similar to the conservation of energy in the sense that they're numbers. I haven't very much time to describe them, but I'll mention what they are. One of them is the momentum. It means if you take all the masses in an object and multiply them by the velocities, for instance, and add it together, that's the momentum of the particles in it anyway. And that total amount of momentum is conserved. The energy and the momentum are now understood to be very closely related, and so I should be in the same column in this conservation law. Another example of a conserved quantity is angular momentum, an item which we discussed some time before. The angular momentum is the area generated per second by objects moving about. For example, if an object is here and is moving, and we take any center whatsoever, then the area, the rate of change, the speed at which this area increases, multiplied by the mass of the object, and added together for all the objects, is called the angular momentum. And that quantity doesn't change either. So we have conservation of angular momentum. Incidentally, at first sight, if you know too much physics, you might think that the angular momentum is not conserved. Like the energy, it appears also in different forms, although most people think it only appears in motion. But it does appear in other forms, and I will illustrate that. You know that if you have a wire and move a magnet up into it, increasing the magnetic field through the flux through the wire, there'll be an electric current. That's how electric generators work. So now imagine that I have, instead of a wire, a disk on which there are electric charges analogous to the electrons in the wire. And then I bring up a magnet dead center along the axis from far away very rapidly up to here. So then now there's a flux change through here. Then, just as in the wire, these will start to go around. And so if this were on a wheel, it would be spinning by the time I brought the magnet up. Well, that doesn't look like conservation of angular momentum, because when it's down here, nothing's turning. And when it's up here, it's spinning. And so we got turning for nothing. And that's against the rules. Oh, yes, you say, I know, there must be another kind of interaction that makes the magnet spin the opposite way. That's not the case. There is no electrical force on the magnet tending to twist it the opposite way. The explanation is that angular momentum appears in two forms. One of them is angular momentum of motion, and the other is angular momentum in electric and magnetic field. And there is angular momentum in the field here, although it doesn't appear as motion, and has the opposite sign to the spin. If we take the opposite case, it's even more clear. If we have just these particles and the magnet here, and everything standing still, I say there's angular momentum there. There's a rotational effect. There's an angular momentum in the field. There's a hidden form of angular momentum that doesn't appear as actual rotation. When you pull this magnet down and take the instrument apart and all the fields separate, then the angular momentum that's in the field has to appear now, and this thing will spin from the... And the law that makes it spin is the law of induction of electricity. Now, the question as to whether it comes in units is very difficult for me to answer. At first sight, you'd say it's absolutely impossible that angular momentum come in units, because angular momentum depends upon the direction in which you project the picture. I said that another lecture, that you have to look at this thing and see how the area changes. If you look at an angle, if you had something turning this way, and you looked at it sideways, you wouldn't see any area changing. And if you looked at it not quite vertical, but just a little bit off, you see that the area changes a little bit different. A little bit different if you come at a small angle. So if angular momentum came in units, 8 units, and then you look not exactly down at the 8, but at a slight angle, it should look like a little bit less than 8. Now, 7 is not a little bit less than 8, it's a definite amount less than 8. So the darn thing can't possibly come in units. This proof, however, is evaded by the subtleties and peculiarities of quantum mechanics. If we measure the angular momentum about any axis, amazingly enough, it's always a number of units. So what to say about this is yes. But it's not the kind of unit like electric charge that you can count them inside. The angular momentum is, although it does come in units in a mathematical sense that the number that we get in any measurement is a definite integer times a unit, we cannot interpret that in the same manner that we interpret this in the case of electricity, that there's this one and see another one. You see those little 6 units in there? You can't see the units, you see, but it comes out always integer anyway, which is very peculiar. Now, there are a number of other conservation laws which are more, that I should include in the list, and I'll just illustrate the type. They're not as interesting as these. They're not numbers exactly. If the laws of physics are nice, and if we were to start some kind of a device off with particles moving, which had a certain definite symmetry, suppose that we had some objects that were like this, and that the exact way that they were moving was such that it was bilaterally symmetrical. Then as the laws of physics go on, and all the collisions and so on, you would probably expect, and rightly so, that if you look at this same picture later, it will be bilaterally symmetrical. So there is a kind of conservation, a conservation of the symmetry character, which should be in the list there. But it's not like a number that you measure, it's just a symmetry character. And below I will discuss it in much more detail in the next lecture. The reason it's not very interesting in classical physics, because the times in which you get such a nicely symmetrical initial conditions is very rare, and it's not a very important or practical conservation law. But in quantum mechanics, when we deal with very simple systems like atoms and so on, their internal constitution often has this kind of symmetry of some sort, like bilateral symmetry or other, and then the symmetry character is maintained, and it's an important law for understanding quantum phenomena. But I should include in the list of all the important conservation laws, but I will discuss it next time. An interesting question is as to whether there is a deeper basis for these conservation laws or whether we have to take them as they are. And that, again, I will reserve for next time. Finally, I would like, however, to mention, to remind you that in making a popular speech on these subjects, there seem to be a lot of independent things. But with a deeper understanding of the physics, of the various principles, there are deep interconnections between the things so that one implies the other in some way. For example, the relation between relativity and the necessity for local conservation, which if I said that without the demonstration would appear to come kind of a miracle. That the statement that you can't tell how fast you're moving implies that if something is conserved, it must be done not by jumping from one place to another. And here I would like to show you that the conservation, or indicate how the conservation of angular momentum, a conservation of momentum, and a few other things are to some extent related. The conservation of angular momentum has to do with the area swept by particles moving. Now, if the radius, if you had a lot of little particles here, and you took the center very far away, then the distances are almost the same for every object. And it doesn't make much difference. So the only thing that counts in the area sweeping, or in the conservation of angular momentum, is the component of motion vertically, say, in this case. So what we would discover is that each mass multiplied by its velocity vertically, added together, must be a constant. Because the angular momentum is a constant about any point, and if that point is far enough away, then it must be only that the sum of the masses times velocities is constant. And therefore the angular momentum implies the conservation of momentum. The conservation of angular momentum implies the conservation of momentum. And that in turn implies another thing, which is the conservation of another item which is so closely connected that I don't put it in the list, which is a principle about the center of gravity. That a mass in a box cannot just disappear here and move over here by itself. That's nothing to do with conservation. You think, well, you still got the mass, and I moved it from here to here. Charge could do that, but not a mass. Let me explain why. Suppose, since the laws of physics are not affected by motions, that this box was drifting slowly upwards. And take a point not far away. Now, as it's drifting upwards, if the mass were here quiet in the box, in the beginning it has a mass here going up and producing an area at a certain rate. After the mass has moved over here, if it's going up at the same speed because the box is drifting, then the area would be increasing at a greater rate because there's a bigger length this way, although the altitudes are the same. But by the conservation of angular momentum, you can't change the rate at which the area is changing, and therefore you simply can't move one mass from one place to the other if you don't push on something else and get rid of the momentum or angular momentum. And that's the reason why the rockets in empty space can't go. But they do go. That's because we have, the rocket is what the center of gravity, that is, if you figured it out with a lot of masses, if you move one forward, you got to move others back so that the total motion back and forth of all the masses is nothing. Now, the way a rocket works is that here's a rocket which shoots some gas out of the back, and here's a gas. You see, beforehand, the rocket's standing still, say, in empty space, and afterwards it shoots some stuff out the back, and then the rocket's going forward. And the point is that of all of the stuff in the world, the center of mass, the average of all the mass, is still right where it was before. But the interesting part has moved out here, and an uninteresting part that we don't care about has moved out here. It is no theorem that says that the interesting things in the world are conserved, only the total of everything. The discovering the laws of physics is like trying to put the pieces together of a jigsaw puzzle. And we have all these different pieces, and today they're proliferating rapidly. And they're lying about. Many of them can't be fitted with other ones. Now, how do we know that they belong together? How do we know that they really are parts of one picture, one at present incomplete picture? We're not sure, and it worries us to some extent, but we get encouragement from the common characteristics of several pieces. They all show blue sky, or they're all made out of the same kind of wood. Thank you very much.